Today we're going to talk about digital fluoroscopy, and you have some objectives that you should be able to answer when you're done reviewing this PowerPoint and reading. Bouchon, chapter 26, talks about your digital fluoroscopy. So digital fluoroscopy has some advantages over your conventional fluoroscopy. One is the speed of the image acquisition and post-processing to enhance image contrast is big. So with your digital fluoro, your spatial resolution is determined by the image matrix and the size of the image intensifier. So the spatial resolution is limited by the pixel size. A 1024 by 1024 image matrix is considered to be 1,000 line systems in DF. So when we're calculating your digital fluoro pixel size, you're going to take the image intensifier size, so either 6, 9, 12, whatever the size is, and divide it by your matrix. Here's an example here. So what is the pixel size of 1,000 line DF system operating in the 12 cm mode? So you convert the 12 cms to millimeters, which is 120 millimeters, and you divide the 120 millimeters by the 1024 pixel, gives you the 0.117 millimeter pixel. So with your digital fluoroscopy imaging systems, they almost look the same as the conventional, except it has a computer that is added, and it has multiple monitors and a more complex operating system. So here's your conventional, very simple system. And it has a cassette loader there. So this is the part of the digital that's different. So as your II has two monitors typically. Here's your ADC and your DAC, and you have memory. So you can see there's a lot more components to it. So the operating console, on the right hand side, there's alphanumeric and special function keys on the right for patient data and communication with the computer system. So there's special function keys for data acquisition and image display, and computer interactive video controls, and a pad for cursor and region of interest manipulation. Some may have roller balls or joysticks or something different. It doesn't have to be a pad. So on the left side of the monitor is used to display the subtracted images, which we'll talk about what those subtracted images look like. So here is your basic, here's the controls, and here's the images that are subtracted. This is within the control room here. So in your digital fluoroscopic imaging system, you have pulse progressive fluoroscopy. So the images from the DF are obtained by pulsing the X-ray beam. During fluoroscopy, the under-table tube operates in radiographic mode. So the tube current is measured in hundreds of MA instead of less than 5 MA in an II fluoro. If energized continuously, it would fail due to overloading of heat, so it would be too hot. Image acquisition rates are 1 per second to 10 per second, which is common. So 33 milliseconds is required to produce a single video frame. Exposures longer than this can result in unnecessary patient radiation and doses. Longer exposures may be necessary to ensure low noise and good image quality, especially if you're dealing with pediatric cardiac. So flat panel instead of an image intensifier. So X-ray times can be continuously varied, so greater dose reduction to the patient. Each time the flat panel is exposed, it is read immediately. So the next image is acquired immediately. Generator must be able to switch on and off rapidly. So the time required for the tube to switch on and reach selected levels of kVp and MA is called integration time. The time required for the X-ray tube to be switched off is the extinction time. So high frequency generators with integration and extinction times of less than 1 millisecond are needed. So this gives you an idea here. You have your 100 millisecond for the whole thing. So 1 millisecond integration time, and then your 1 second extinction time. 1 millisecond, sorry. So your duty cycle, what that is the fraction of time that the X-ray tube is energized. So here, that's the 100 milliseconds. With the figure below, you can see that the X-ray tube is energized for 100 milliseconds, every second. So this represents a 10% duty cycle. So it's really important in reducing the patient dose. So the image receptor in digital fluoro is a charge coupled device. We use that instead of a TV camera tube. Its sensitive components of the CCD is a layer of crystalline silicone. When silicone is illuminated, electric charge is generated, then sampled, pixel by pixel, and manipulated to produce a digital image. It's mounted on the output phosphor of the II and is coupled through fiber optic or a lens system. With the lens system coupled CCD, a sample of light is measured and used to drive the automatic brightness stabilization system. So here is your charge coupled device. And you can see here your charge coupled device with your fiber optic bundles on your output phosphor. And this is your charge coupled device, what's on the inside, so complex. And you can see how it all fits together here. So this is the lens system, so you can see the lens and coming out to the ABS to your CCD up top. All right. Advantages of charge coupled devices. So there's high spatial resolution is determined by the physical size and the pixel count. So 1024 matrix can produce a 10 line pairs per millimeter. High signal to noise ratio, so low levels of electronic noise. High DQE, so greater sensitivity to light, and no spatial distortion. So the TV camera tubes can show spatial distortion described as pincushion or barrel effect, which does not occur with digital fluoro. Also, there's no warm-up required, no lag or blooming, no maintenance, unlimited life, unaffected by magnetic fields, and that is important when you're using magnetic tips on catheters. If you get into IR or cath lab, you'll know about that. And there's a linear response, and there's lower patient dose due to that pulse. So the charge coupled device's most important feature is its linear response. So it has a wider dynamic range and better contrast resolution than your II. So image receptor, so you have a flat panel image receptor, so the FPIR. So it's composed of cesium iodide and amorphous silicone pixels. They're much smaller and lighter and easier to manipulate than the II. So easier patient manipulation for the radiologist or the technologist, and there's no cassettes. So your flat panel, the advantages are distortion-free images, so the center to periphery are exactly the same, unlike with the II. Constant image quality over the entire image, so same thing, so the center and the periphery are exactly the same with your quality. Improved contrast resolution over the entire image, high DQE at all radiation dose levels, rectangular image area coupled to similar image monitor. So the field is rectangular, similar to the monitor, which is great. And it's unaffected by the external magnetic fields. So when you're looking at the image display here with conventional fluoro system, the disadvantages are that you have interlaced modes, so it degrades the image, the digital image, and signal to noise is about 200 to 1. You have, background electronic noise, sorry about that. And with your digital fluoro system, you have progressive mode, and it sweeps continuously, so you have a sharper image with less flicker, and your signal to noise ratio is 1,000 to 1. So this gives you an idea here. We're at the 1,000 to 1 signal to noise, and you can see here with the 200 to 1 the difference here, so it's a lot more sensitive. So the tube with the 1,000 to 1 SNR provides 5 times the useful information and is more compatible with computer-assisted image enhancement. So digital subtracted angiography. So characteristics of a DF system that the computer controlled include the image matrix size, the system dynamic range, and the image acquisition rate. So the output signal from the image intensifier digital image receptor is transmitted to an analog to digital converter, so an ADC. So accepts the continuously varying signal analog and digitizes it. So the flat field is already digital. So to be compatible with the computer, the ADC must have the same dynamic range as the digital system. So an 8-bit ADC would convert the analog signal into values between 0 and 255. A 10-bit ADC would be more precise. ADC ranges from 0 to 2 to the 10th or 0 to 1023. If stored occurs in primary, so it can be as rapid as 30 images per second. If matrix is doubled, it'll be 4 times as long for the acquisition. So image formation. So image contrast can be enhanced electronically by subtraction techniques. So there's temporal subtraction and energy subtraction. When both are combined, it's called hybrid subtraction. So temporal subtraction is more frequently used due to the high voltage generators limitations associated with the energy subtraction. So temporal subtraction, so it's a number of computer-assisted techniques whereby an image is attained one at a time, is subtracted from an image obtained at a later time. So if contrast is introduced, the subtracted image will only show the contrasted vessel. So there's 2 different types. There's mass mode and time interval difference mode. Mass mode, patient is positioned under fluoro, the power injector is loaded and programmed, the image system is changed from fluoro mode to DF mode. You increase the tube current of 20 to 100 times of that of the fluoro mode. Activation program of pulsed image acquisition. So the injector is fired, and after 4 to 10 seconds, and before the bolus of contrast reaches the anatomical site, pulse exposure is made. This is the masked image. So the image is now stored in the primary memory and is displayed on the video monitor. The masked image is followed by a series of additional images stored in adjacent memory locations. While being acquired, the masked image is subtracted from the image and displayed on the second monitor, so monitor B. Subtracted image is displayed in real time and is stored in the memory. So this gives you an idea. Here's your mask, and you can see it's taking the images and then it's subtracting out the bone and everything else that was the tissues that were in there. So here's posterior circulation of the brain. Here's your pre-injected mask. Here's your post-injected image, and then it subtracts it so you only get the contrast. So time interval difference mode produces a subtracted image from progressive mass in following frames, so it does each one at a time. Energy subtraction. No special demands on high voltage generators, uses 2 different X-ray beams alternatively to provide a subtracted image that results from differences in photoelectric absorption. So this is the most important part. It uses differences in energies to see photoelectric absorption. So abrupt changes in photoelectric absorption at the K-edge of the contrast media compared to soft tissue and bone. When the incident X-ray energy is sufficient to overcome the K-shell energy, electron binding energy of iodine, it is abrupt and large increases in absorption occurs. It's known as K-edge absorption or K-absorption edge. So you can see here, this is road mapping. Mask images are acquired and stored. Contrast is injected. Subtracted images are acquired in the digital subtraction. As the catheter is fluoroscopically advanced, the image is formed by subtraction from a second mask. Now, doses compared to conventional versus digital. So in 5 minutes of fluoro, you can see conventional we have about 200 or 20 rad, and with digital you have about 10. Spot films in normal mode, you have 0.6 rad compared to 0.2, and 3 spot films, Mag 1 mode, you can see the difference there. So the total dose using digital is about half, which is really, really good. So please read your Bouchon chapter 26. This is where I got all of this information.